and graph these. They're weird, right? Log base 1/10 of x. That's strange, right? So you would say like 1/10 to what power is whatever x is. Kind of interesting way to look at it, but rather than graphing these by hand, I prefer to let the technology do the talking, right? And remember, you can use your log base key, right? Math, and then go all the way down to log base. But I'm going to go ahead and change the base so that it doesn't matter what calculator you have. You can do this with any graphing calculator. So let's go ahead and graph the first one, which is log base 1/10 of x. So if I use my change of base, that's going to be log of x divided by log of 1/10. Right? That's how I change it to log base 10. And I can hit graph and see what that's going to look like. Ooh, it's up inside down. That's what my son used to fall upside down when he was a little baby. It's up inside down. Yeah, it's cute. It's nice mouse. Fifth grader? Huh? I don't think he's gonna watch this. Hopefully. Alright, the other one was log base 1/2, right? Of x, so we're gonna go log base x, log base 10 of x divided by log base 10 of 1/2. And then I'm just going to keep going because we have the log base 1/5, it's an xy. So I'll go log base x, log base 10 of x rather, again. Divided by log base 10 and we hit graph. And whoa, what's going on? If we compare these to our previous graphs, what has happened? You might have to use some of your terminology that you learned back in geometry, right? It's a reflection, and it's a reflection about what? About which line? Yeah, you can say the horizontal axis, like an x-axis, right? You could say about the line y equals 0. That's a lot more. That's the most correct way to say it. It's actually the most useful way to say it when you get in your higher levels of mathematics. So, take a moment to sketch those. Okay, so you should have those sketched, and let's go ahead and talk about the relationship. As we mentioned, we said that it was a reflection. So it is, ooh, I'm just going to go with it. So you could say the x-axis, but even better, let's say the line y equals 0. Huh? Yeah. Why does this happen? Here we go. I'm gonna do a little weird thing here. So let's talk about it. Let's look at first the function, or actually let's just look at this function here. Log base 1/10 of x. What in the world is going on with that? So and they don't give us a lot of room to do the math required for this, but it's okay. So log base 1/10 of x. Let's go ahead and write that as a log base 10 logarithm. So that would be log base 10 of x divided by log base 10 of 1/10. Well, what's going on here? That's log base 10 of x divided by, isn't that log base 10 of 1 minus log base 10 of 10, right? We're going to use our property of logarithms. So split that bad boy up, that's at our denominator. Well, log base 10 of 1 is what? So 10 to what power is 1? 0 power is right. So that's 0. And log base 10 of 10 is what? 10 to what power is 10? 1. 1. Weird. That's super weird. So then isn't this just negative log of x, right? If you divide something by -1, it just becomes negative. And that makes sense, right? When you make something negative, you reflect it. When you put a coefficient of -1, it reflects it about the x-axis, right? Think about x squared. Think about that parabola, right? When it's x squared, it's opening up. Negative x squared is pretty much the same thing, but it's a reflection opening down. So it makes sense why each one of these were reflections, if we use our properties of logarithms. All right. Now we're going to use some weird function notation that we haven't seen in a little while. We're going to talk about if we have f of x, what is f of x, or f of kx, right? What does that mean? Well, let's look at a few examples. If we had y equals, really that y equals f of x is saying y and f of x are kind of the same thing. They are the same thing, okay? There's different notations, okay? Well then, what if I had y equals f of 2x? What does that mean? What that means, this means that everywhere you see an x, plug in or substitute 2x, right? I guess that's a capital because it's actually expensive. So what do? If I plug 2x in here, I wind up with just 2x, right? So we're looking at the function y equals 2x, right? What happens to that? What's the difference between y equals x and y equals 2x? Well, let's think about the graph, right? Or actually, let's just go ahead and get our tools out that we have. Whoa. So what's the difference between y equals x and y equals 2x? What? One should be steeper than the other, right? It makes the graph steeper. It increases the rate of change, right? It makes it increase faster. If our change is an increase, it's going to make the increase go faster, right? If our change is a decrease, it's going to make it decrease if we put a coefficient in. And we can see that, for instance, with if we also look at y equals we'll just go ahead and write if f of x is x squared, right? Then f of f of 2x is equal to 2x squared, right? Which is 4x squared. See what I'm doing when I do that? It's just like saying f of 2, right? If you're asking what f of 2 is, you plug in a 2 everywhere you see an x, right? All we're doing now is we're plugging in variable quantities instead of just number quantities. So what's the difference here? Let's get rid of these guys, and let's look at the difference between x squared and 4. So it's been shrunk, right? Horizontal with a horizontal shrink, or you could call it maybe even a dilation if you wanted to. Yeah. If you want to use your geometry terms, you call it horizontal scaling, right? But the main idea is that the rate of change has increased. Yeah. You know what I'm saying? This one, the red one, is 4x squared, and it has right. It's decreasing at a much faster rate and increasing at a much faster rate depending on which side of your parabola you're looking at. So let's answer our question now. What is going on? We could say it's a horizontal scaling. Or a, some people say squeeze. It depends on who's teaching it to you. There are a lot of different ways that you can have that experience. But the thing that is always true is that there is an increased rate of change. That, no matter the terminology, is always true. So that kind of gets away from the terminology of squeeze or dilation or scaling or whatever. Bottom line, the rate of change is increased. All right, hey, let's graph these points. Hey, let's not do it by hand. Let's not do it by hand. And in fact, let's go ahead and go for our graphing calculator. So log base 10 of 10x, log base 2 of 2x, and log base 5 of 5x. Again, I'm going to go ahead and change the base on those so that we can put those into any calculator. So log base 10 of 10x was easy enough to do. I did not have to change the base, right? I don't want to see there. I think it'll graph it without it, but it bugs me not to have a hanging parenthesis. All right, so log base 2 of 2x, I'm going to write that as log base 10 of 2x divided by log base 10 of 2. That's how we would change the base on that bad boy. Boom. The other one is log base 5 of 5x. So we're going to go log base 10 of 5x divided by log base 10 of 5. And we hit graph. And it looks like maybe it was a vertical scaling, right? Like it was stretched out vertically. And when I first looked at this, that's what I thought. But I was wrong. And I was able to figure out why I was wrong when I compared the graphs to their parent function. So the parent function of log base 10 of 10x is going to be log base 10 of x. So let's compare those two parent functions. And get rid of all this other stuff. Jot that down though. Go ahead and jot that down where you're supposed to have the graph. I'll give you a moment to do that. Alright. So now I wanted to talk about what's actually going on. What is the transformation that's happening there? So let's go ahead and graph what would be our parent function for a log base 10 logarithm, which is log base 10 of x. And you see that it wasn't actually any sort of like dilation or stretch or anything like that. It's actually a translation, right? It's a vertical translation. It's actually translating it up 1 unit, isn't it? If the red is our parent function and the blue is log base 10 of 10x, then what we've done is we've translated 1 unit in the positive y direction. Okay, let's go ahead and I think we're going to have to justify that, aren't we? That's on the next page. Yay, all right. So what is the transformation? It turns out that we discovered by inspection that the transformation is a translation of 1 unit. All right. So for some reason our answers don't agree, right? We said that if you take something and you put like kx there, right? It should be some sort of a scaling, right? We should have some scaling occur. No scaling occurred here. What happened was we shifted it up. So why did that happen? Let's go ahead and look at log base 10 of 10x and figure out why in the world that happened. Well, isn't it the case that I can write this as log base 10 of 10 plus log base 10 of x? And what is log base 10 of 10? 1. So 1 plus log base 10 of x, and it makes sense that this would be a translation, right? What happens when you, if f of x is, if f of x is x, then if f of x plus 1, that's x plus 1, right? That's a shift up, right? So this is also a shift. And then, additionally, what happens if I have f of x equal to x squared, then f of x plus 1, and that's also a vertical shift. I'm introducing you to some function notation because I'm going to put something up that's not in your book right now. A little extra stuff. So it's in your homework, but not in your lesson. So I just want to talk real quick about what happens. Yeah, if I say f of x is x squared, right? And g of x is x plus 1. And I want to know what is f of g of x. What this says is everywhere you see an x, an f of x, plug in g of x. Yeah, it's not that bad of a concept to get, but for some reason it's missing. So I want to get it in there for you. Boom. So that's what it is, right? I just substitute x plus 1 instead of x, right? So if f of x is equal to 2x squared minus x plus 1, and g of x is 1 over x. Oh, I don't want to put in this. So something a little more complicated. Let's find f of g of x. And this is called function composition, when you put a function inside of a function. So that's going to become 2 times 1 over x squared minus 1 over x plus 1. And we do have to simplify these, so this becomes 2 over x squared minus 1 over x. Not too bad. I put one problem on your homework like it just so that you can see it, get exposed to it, and use it a little bit. In your tests, I use a lot of function notation just to get you used to it. You should feel comfortable. Cool, and we have a few minutes to move on to lesson